Once we enter the realm of the very small, classical physics crumbles and falls apart. Gravity, mass, motion, and position are no longer predictable, and uncertainty and improbability rule. What started as a quest to build a better light bulb has now become a battlefield of new math and shocking conclusions, putting some of physics' greatest minds to the test. In the 1920s, physicists, including Max Born, Niels Bohr, Erwin Schrödinger, Paul Dirac, and Werner Heisenberg, built upon this radical new understanding to further describe the nature of the subatomic world. In 1926, Werner Heisenberg began to develop a theory based on wave mechanics, using some unfamiliar equations. Working closely with Niels Bohr in Copenhagen, Heisenberg discovered that whenever one tried to measure position and velocity of a particle at the same time, imperfections and errors occurred. His startling conclusion was that these errors lay not with the measurer, nor with the instrumentation, but were in fact fundamental to subatomic particle behavior. Only 26 years old, Werner Heisenberg became a leader in the new quantum revolution.
The uncertainty principle of Heisenberg was really a sharp turning point in the historical development of quantum mechanics, because in the early days you could have still held on to a thread of hope that these new quantum ideas might somehow not be as different from classical physics as they were appearing to be.
According to quantum mechanics, you can never simultaneously know the exact speed and location of a particle because the particle is also a wave.
But with the uncertainty principle, Heisenberg showed that you cannot know the position and the speed, or more precisely, the position and the momentum. It's called speed, close enough. You can't know the position and the speed of a particle. But positions and speeds of particles, that's the heart of classical physics. And he is saying that you can no longer have access, you can no longer specify those two features simultaneously. That means the classical world really differs in a profound way from the quantum description that is emerging from the pursuits in the early decades of the 20th century.
The Roaring Twenties were a time of radical political movements and unprecedented industrial growth. New inventions, music, and art all burst upon the scene. In Copenhagen, the next new wave of quantum mechanics was born. Niels Bohr and his colleagues formulated new rules that firmly rejected the classical laws of cause and effect. According to the Copenhagen interpretation, classical measurements were no longer possible in a purely probabilistic subatomic realm. Albert Einstein said, "Impossible." To him, this view of the world was not only disturbing, but it had to be wrong. The great physicists, Einstein and Bohr, publicly wrestled with this new idea of quantum mechanics, each trying to outwit the other, as if playing a game of intellectual ping pong. Einstein proposed experimental systems by which measurements could be determined. Bohr shot back with proof of indeterminacy in the system. Einstein was convinced that a probabilistic theory could never explain the natural world. He believed in what he called an invisible piper, and that everything in the universe danced to its tune. In Einstein's view, quantum mechanics might be a good step towards a unified theory, but it could not be complete. He famously said, "God does not play dice." Bohr countered, "Einstein, stop telling God what to do." Although the outcome has been debated, many agree that Bohr was triumphant.
Well, the wonderful thing is that when we think about quantum uncertainty, most people interpret that as meaning that everything's uncertain. We'll never have certainty in the world. once we embrace Heisenberg, and that's not true. What Heisenberg was saying was certain ideas that we held dear in a classical perspective, those ideas can no longer simultaneously be certain in the quantum domain. You can't know where the electron is and how fast it's moving simultaneously. But can you know where an electron is? Yeah, you can do that with certainty in quantum mechanics. Can you know about its momentum? Yeah, you can do that with certainty too in the quantum domain. There is certainty in quantum mechanics. It's just not the same certainty that we were used to from classical physics. So you don't throw precision out the window when quantum mechanics comes along. You simply change the features of the world that you thought you could describe simultaneously with certainty. Now you realize that you can't.
Quantum mechanics proved increasingly maddening to Einstein. Not only did Newtonian rules get tossed, but Einstein's theories of relativity and gravity were soon under fire in the quantum world.
The key idea of Einstein's general relativity is that gravity needs to be described in a new language. Not the old Newtonian language of one object somehow reaching out across space and pulling on another with this force of gravity. Einstein's new image is that gravity is associated with warps and curves in space. So the way the sun pulls on the Earth, according to Einstein, is that the sun warps the environment around it, and then the Earth moves through that warped environment, and curves in space, in some sense, nudge the Earth into the orbit that we are familiar with from observations. So it's a new way of thinking about the underlying means by which gravity exerts influence. It exerts it by warps and curves in space and time.
But if we shrink Einstein's picture of space, time, and gravity down to the atomic world, what happens?
Well, there is a deep conflict between Einstein's general theory of relativity and quantum mechanics. And one way of thinking about it is to realize that because of the uncertainty principle in quantum mechanics, there's a sense in which, in the microscopic domain, there's a tremendous amount of activity. Because, unlike in the classical world, we can't nail down all features in the microscopic world because of the uncertainty. And that means there's a way in which those features are fluctuating, roiling, creating a tumultuous domain in the quantum realm. But Einstein's vision of gravity is anything but tumultuous. Nice, gentle warps and curves in space. And it's this gentleness of the general theory of relativity versus this tumultuous quality of the world according to quantum mechanics that makes the two theories just sort of smash into each other, making it very difficult to meld them together into one consistent whole.
This was too much for Einstein, who abandoned quantum mechanics as a completed theory and tried to develop a unified field theory up until he died.
There doesn't have to be a unified theory. There are those who suggest that that is a order that's too tall. We're asking for too much. It's fine to have general relativity over here, talking about big things, stars and galaxies, quantum mechanics over here, talking about small things, molecules, atoms, and particles, and just leave well enough alone. Don't try to make some harmonious union. You've gone far enough. The problem is the universe itself seems to tell us that's not far enough. Because when we study the physics of exotic objects like black holes, we encounter domains like the center of a black hole where matter has been crushed to a very small size, needing both gravity and quantum mechanics. You can't just keep them separate. The Big Bang, everything crushed to a very small size. You need gravity and quantum mechanics. Again, you seem unable to keep them from talking to each other. And when they start to talk to each other in the conventional formalisms of physics, it doesn't work. The math breaks down. Nonsense emerges. So that suggests to us that this nice notion of keeping them apart is not the answer. You got to let them come together. You got to find a theory in which they can talk to each other sensibly.
Is there a theory that can reconcile the tiny subatomic scale of particles with the very big scale of planets and stars?
We do have a theory on the table. It's been on the table since the 1960s, but in its modern version since the 1980s, called string theory. And string theory, at least on paper, finds a way of stitching together quantum theory and general relativity.
String theory attempts to explain gravity and other forces at the subatomic scale by concluding that particles are strings and forces are created by their unique vibrations.
So in string theory, the forces of nature arise from the string vibrational patterns. So in quantum physics, we've learned that every force is associated with a particle that transmits that force. The most familiar example is the electromagnetic force, which is transmitted by the photon, a little tiny particle of light which transmits the electromagnetic force from place to place. Now in string theory, the photon is just a string vibrating in one particular pattern. So the carrier of the electromagnetic force, the photon, is just a string vibrating in one pattern. And that idea, we believe, applies to all the other forces. Gravity, transmitted by a little bundle, little particle of gravity called the graviton, which would be a string vibrating in a different pattern. The nuclear forces, strong nuclear force transmitted by the gluon, is what it's called. In string theory, the gluon would be a string vibrating in a different pattern still. So it's a beautiful structure in which all of matter and all of the forces, they have the same explanation. They all arise from the different vibrational patterns of a string.
One of the more stunning predictions of string theory is that our universe is made up of extra dimensions. Space, according to classical physics, is three-dimensional, based on three coordinates, x, y, and z. Einstein introduced the fourth dimension, time, into his general theory of relativity. String theorists have calculated that as many as 6 extra dimensions make up our world.
Well, we're at a very interesting place today with string theory. On the one hand, we have a theory that on paper is able to put gravity and quantum mechanics together. Huge, huge, huge achievement. On the other hand, we've been unable so far to extract from string theory predictions that we can test to determine if the theory really describes our world or not. Moreover, in the process of analyzing string theory, a number of strange ideas have emerged. The possibility of extra dimensions of space, the possibility that ours might not be the only universe. Very strange claims on the nature of reality, and therefore, to embrace those claims, you need some powerful observational or experimental evidence to drive you toward this new picture of reality. So we're at, in many ways, a potent moment. Our hope is that the Large Hadron Collider might see some indirect signal of string theory, possibly the production of what we call supersymmetric particles, a class of particles that string theory suggests should be there but yet have not been found. If that machine turns up those particles, that will be a big boost, circumstantial, but a big boost that string theory is going in the right direction. There are other signatures that might happen too, possibly the production of little microscopic black holes or missing energy in signals that emerge from the collider, suggesting that particles may have been ejected into the extra dimensions which the theory claims should be there. I think it is possible that within the next 20, 30 years we might have a plausible theoretical understanding of how the universe came to be. Now that might be hubris. Maybe it's going to take 1,000 years. We don't know. But the rate of progress on penetrating deep questions of the cosmos, the nature of space and time and how it evolves, the rate of progress suggests to me that it's not unreasonable to hope that in a reasonable time frame we'll have a plausible explanation.